Okay, so this is going to be our first example of a Taylor series free response that we'll do in this virtual setting. This actually is a problem I assigned a while back that we never hit a point we could collect. It's a really good one, and I think it gets at a number of layers that the AP typically asks in terms of Taylor and Maclaurin in this specific case. But of course, Maclaurin is just a specific case of Taylor. So what they've done is they've given us a graph and they've called it our function. That's kind of our parabola looking thing there. And then they said they put in a tangent line. And so we have to understand that that line in the diagram is a tangent line. They've then given us selected derivatives evaluated at x equals 0. So they've given us the second, third, and fourth derivatives. And that table got a little bit cut off over here, but you can see, let's see, right there is our second, third, and fourth derivatives. We're going to be doing a Taylor around x equals 0 or a Maclaurin series, and they'll use those. You can see how they kind of use those interchangeably throughout the problem. We're going to be focused on the values at 0, so right there. So in this table, they've given us the second, third, and fourth derivatives, which means we also need to know, or will need to know, the function evaluated at 0, and we're going to need to know the first derivative evaluated at 0. So we're going to have to use the graph for that. So the function evaluated at 0 is 3. That's just where I put that dot. And the first derivative evaluated at 0 is whatever the slope of that line is. So we can just count that off the graph. It's got a drop or a rise of -2. So we're going down 2, and it's got a run of 1. And so my slope of that tangent line is -2. So I've got two other pieces of information I can kind of add in. I'm going to switch over to a different color to start the problem. So these are just kind of some base building pieces. So the first part A, it says write a third degree Taylor polynomial. So we're looking to get up to the place where we've got a cubic in the expression. So a third degree Taylor polynomial. Well, in general, what a Taylor polynomial looks like is a function defined as an infinite summation from 0 to infinity. And we've got the nth derivative evaluated at a, which in this case a is 0, and we've got x minus a. So actually I'm going to put a little 0 right there. We've got x minus a, which in this case again is 0, to the n over n factorial. That's what our generic structure needs to look like. And this first one is just asking us not to come up with a generic, but to actually just list out terms. So we'll start with the 0th derivative, or the function value. That's 3. So our first, this is part A, our first would be 3, first term. And then we're going to add a -2. So that means we're going to subtract. So it looks like this thing might be alternating, times x to the first power. Because in this previous term it was x to the 0 power. So now it's x to the first power over 1 factorial. So I'm not going to write that in there. I'm just going to leave it as -2x. Then my next derivative is a 2. So that's coming from, I'm sorry, that's n equals 2. So it's actually a 3. So let me take and erase that 2 and we'll make it a 3. So there's our second derivative, our third term as we're writing. And that's going to be x squared, and that would be over 2 factorial. So I'll write the 2 factorial in there. Technically speaking, I guess I could throw these down there and that wouldn't be wrong. We don't need them, but they're there. And then we're going to finally do one more term, which is a -23 halves x to the third power over 3 factorial. That's our generic, and in truth, we're good with that. We're going to do some things with it though, so I'm actually going to simplify that structure down a little bit. So we'd have 3 minus 2x plus 3 halves x squared minus, let's see, this one, 3 factorial is 6. So I've got 23 halves times 1/6 x cubed. And if I then simplify this, we've got 3 minus 2x plus 3 halves x squared minus, let's see, this would be 23/12 x cubed. And that would be our third degree Taylor centered around x equals 0, or our third degree Maclaurin for the function as they've defined it. And again, we're using a blend of the graph as well as the table that they've given us. Okay, so let's move to part B. Part B is saying write the first 3 terms of the Maclaurin series for e to the x, and then write a second degree Taylor for e to the x times f of x around x equals 0, or a second degree Maclaurin. So we're going to be doing two things on this one. First, we've got to write the expression for e to the x. If you can just remember this, or you know this, this is one of those that the AP hits very frequently and just expects you can remember. If you have to take the time to actually construct it, you're probably using a little time you shouldn't be or don't need to. The derivatives for e are all e to the x, so every derivative is equal to e to the x, and then we're going to evaluate that at 0, so e to the 0 is 1. So every derivative for e is 1, which means if we fit it with this structure up here, then we're going to have a 1 and then x to the n over n factorial. And it's not going to be alternating, so this is our generic structure for e. And they are expecting here that you're just pulling that amount or that value out. So if we put a 0 in, we get x to the 0, which is 1, over 1 factorial, or 0 factorial, which is 1. Then we get x to the first over 1 factorial, and we get x squared over 2 factorial, and that's it. That's the second degree Taylor, which is what it's asking there. And of course we could streamline that and call it 1 plus x squared over 2. And in truth, you can just give them that. You don't need to actually show them where it comes from on e to the x. They're then asking for us to combine infinite functions. So they're asking for us to take e to the x, multiply it by f of x, which we came up with above. So that's these two multiplied together. And to write that as a second degree Taylor polynomial for e to the x f of x around x equals 0. So we're going to take those two and multiply them together. To do that, we're going to have to, really you're lining up an infinite set of terms here, and you're lining up an infinite set of terms here. But in truth, we don't need to even do the amount that they've given us, because if you think through the arcs, and I'll switch colors here, that first arc is going to hit all these pieces. That second arc going to do the same thing. And by the time you start drawing in the third arcs, which are going to come from here, to get to a second degree, you only need one. You only need to hit the 3 with it. Because once it hits the next term, you're going to get to an x to the third power, which we're not after. So e to the x times f of x, if I take that 1 and I arc it through, to get up to a second power, it's going to hit 3, it's going to hit 2x, and it's going to hit 3 halves x squared. Then I'm going to take the x, that's the second thing along the way, and that's going to run into 3 and 2x. Anything more than that, and I've gone over the x squared power. And then finally, I've gone to x squared over 2. That's my third thing here. And that's going to only hit the 3 before, again, it would get to a power that I'm not going to be asked to use. So here I've got 3 minus 2x plus 3 halves x squared. Here I've got 3x minus 2x squared. And here we've got 3x squared over 2. And I'm going to combine all of those things together. So we're going to add all those things together. And let's see, I've got the 3 all by itself. I've got minus 2x and plus 3x. So there's our 3 all by itself. And I've got minus 2x plus 3x, that's plus x. And then I've got a bunch of x squared terms, right? So I've got 3 halves, I've got 3 halves. You put two sets of 3 halves together and you get 3. I'm then going to subtract 2x squared from it, so I'm going to get a plus x squared. And so that is going to be my combined ex times f of x. Okay, so let's shift gears to part C. So part C on this thing, we'll go climb way back up here. Let h be the function defined as the integral of f of t dt, and then find an approximation for h of 1. So we're going to integrate this f function that we found. So this thing right here that we found, we're going to be integrating that. So in part C, we're going to be integrating that expression and then evaluating from 0 to 1. So we're going to be evaluating that thing from 0 to 1. So, and they want us to use t's, which makes it a little tricky, and I'll switch to the black on this one. So on C, we're going to be integrating from 0 to 1, 3 minus 2t plus 3 halves t squared minus 23 twelfths. What would that be? T cubed. And then we're going to go dt, and we're going to integrate from 0 to 1. And I think if you had the x's in there, you'd be okay, but they did specifically set it in terms of t, so let's just operate with that. So if we integrate this thing, we're going to get 3t minus t squared, that's just integrating each piece, plus, let's see, this would be 3t cubed divided by 3, so that would actually be, or 3 halves t cubed. So that'd be 3 halves t cubed divided by 3, so that would just knock out the 3 on top, and we'd have 1 half t cubed. And then this one, we're going to go minus 23 twelfths t to the 4th divided by 4, so that's going to be 23, 12 times 4 is 48, so I'm going to get a 48 on the bottom, t to the 4th, and evaluate from 0 to 1. Just as a quick check, 0 is going to go in and 0 all those out. So it's going to knock out all those terms. 1 goes in, and obviously we're just going to replace the t with a 1. And this is a no calculator question, so we are asked to juggle some fractions, not the end of the world. 3 minus 1 is 2. Then we have to do the half and 23 48ths. I think probably let's just put everything over 48. It's not that hard, so we'd have 96 48ths. We have 24 48ths minus 23 48ths, which is kind of nice. 24 and 23 are going to just give us 1. So we have 97 over 48. Or, if you wanted to get wild and crazy, you could write that as 2 and 1/48. And that value, either one of those values, would be what they're after on this particular problem. They're then going to ask us for an error bound. So on part D, they're saying we've got the Maclaurin series converging. It's known the individual terms alternate sign and decrease. So they're keying you in to know it's an alternating series test. And they're saying the alternating series bound, we use it to show that we're differing from the actual value of h of 1 by at most 0.45. In other words, it's asking you to look at the next term. So we didn't actually integrate one of those, which means we've got to go do that. So this last unused thing right here, the 4th derivative being 54 is where this finally comes into play. They didn't have you write it, and I'll switch colors again. On this first one, we could have written in another term, and up till now we haven't needed it, but it would have been a plus. And let's see, it would have been a 54 x to the 4th over 4 factorial. Again, to be clear, we did not need that yet, but we are going to need it to do the error bound. So we're going to take our 54 x to the 4th over 4 factorial. So there it is. And we're going to say, well, what if that had shown up at the end of this thing? So what if that had sat right here? Well, we would have integrated that, right? So we would have integrated this expression, and we would have had 54x to the 5th over 5 times 4 factorial. And certainly you can make the acknowledgement that 5 times 4 factorial is 5 factorial, but they're not asking for you to do that. They're just asking that we evaluate this thing from 0 to 1. In essence, plug a 1 in. So 54 over 5 times 4 factorial, and demonstrate that that is below the 0.45 threshold that they gave us. So show that's below 0.45. Well, yeah, just making sure that's 0.45, and it is 0.45. So then we're going to say, okay, well, how do we show that? Well, let's see, 54 divided by 5 times 4 factorial. 4 factorial is 24, so we've got 5 times 24, which is 120. So we have 54 over 120, and we need to demonstrate that that's below 0.45. And we have to do it without a calculator. So 54 divided by 120, well, those can both be divided by 2, I guess. So that would be 27 over 60. And we need to somehow show that that is below 45 over 100. That one gets a little tricky. The way it's presented here, it would be tough to weigh these two, so let's boil them down a little further. Let's divide the 27 and the 60 by 9. Well, that's going to give us 3/20. And let's divide the 45, let's divide them by 3. That's going to give us 9/20. Then we divide the 45 and the 100 both by we could divide those both by 5, and lo and behold, we get 9/20. So this is actually equal to it, and I think the language says this is okay because it's at most in the language, which can be a less than or equal to sign. So that demonstrates that the error bound is at most 9/20. The solutions to this in print will be posted as well on the resources folder. but this is the actual work through of the problem.